So, welcome. My name is James Wormold. I'm a writer here at Europa Science, publisher of Imaging and Machine Vision Europe. Edge computing is transforming image processing in machine vision systems. In today's Visionaries web panel, we'll be discussing how, by moving data processing closer to the source, companies can reduce latency and improve efficiency with real-time decision making. This online panel will explore and discuss how edge computing can optimize machine vision applications to deliver a competitive advantage. Joining us to discuss the topic in real time, we've invited both Giuseppe Garcia, co-founder and HW R&D Director of Digital Systems at Accelera AI, and Faisal Kamran, who's both a Principal Technology Analyst at Sony and, even more impressively, one of our own Photonics 100 honorees. Welcome, gentlemen.
Thank you. Thank you, James.
Thank you.
On the subject of the Photonics 100, by the way, nominations are now open for next year's cohort, so make sure you get down to the Photonics 100 section of our sister title, electrooptics.com, after the webcast, to tell us who you think truly deserves to be recognized as an innovator, boundary pusher, out-of-the-box thinker, or all-round R&D rock star of photonics. Before we begin with today's events, let me point out that the panel discussion will be available to watch on demand alongside others in the Visionary series on the Imaging and Machine Vision Europe website for 12 months after today, in case you'd like to recap any of the information. If you're choosing to watch live, however, you're able to send in your own questions to our panel. Do that at any time using the questions tab at the bottom of Zoom there, and I'll throw them over to the panel when we have a break. Before that, let's get started with the first question. I'm going to come to you first with this one, Giuseppe, so get ready.
Sure.
So tell me about some of the common challenges that you're involved with, that are involved when implementing edge computing for image processing. And is there any advice that you've got that you can give us on how best to overcome them?
Thanks for the question, James. Let me start with few facts. Edge device operated with limited processing power and memory compared to the cloud server. So AI models that you deploy on this platform must be optimized to run efficiently and on less expensive hardware. Power envelope, the second fact is power envelope is a big constraint for those systems. Typically, they run on battery or physically, they are placed on boards on a relatively small box if you are talking about gateways and not really to the sensor. Third fact, AI models to be deployed are becoming more and more complex. We are talking today about billions of weights. So this means explicitly more compute. So if you put together those three facts, we are going to into the direction in which we need more compute, more efficiency, and more cost-effective solution. So this means that you need something that, from a hardware point of view, is something new, and the GPU that today are widely used probably are not enough. So we are going to a space of hardware accelerator for AI edge devices. Accelera is providing a platform in that respect. Now, let me go more deeply in some of the challenges that you find and what kind of solution we adopt so far. So first, hardware resource limitation. And the problem here, the challenges are to maintain numerical accuracy of a floating point compute, but at the same time mapping or quantize our neural network into something that is more light in terms of compute, typically int8. What does it mean? Think about a floating point neural network that needs 100 megabytes of model of memory. In int8 will become only 25 megabytes. And less processing is going on for int8 with respect to floating point. So quantization is something you need to keep in mind if you are deploying at the edge. graph pruning, graph manipulation to prune some of the operation to make it more efficient in terms of deployment into your chip, compression data. So, and most importantly, have a stable and reliable software stack with the right verification tool to control the accuracy. So to do this downscale in terms of computing without losing accuracy. And this is embedded into on the top of this, you need also a real-time compiler to actually use the, let's say, the resource and balancing the workload on your chip. Okay, so this is for hardware resource limitation. You have other aspects and other challenges, low bandwidth or absent connectivity. So think about models which has interaction compute that it goes to the cloud or goes locally, and you need to decide how to sync data correctly. So you need to manage what intermediate results that need to stay at the edge or things that need to be shared onto the cloud and take into account that your connection cannot be reliable. Efficiency. You have a limited space to dissipate. It's a thermal problem here. And so forget about cooling system based on liquid cooling, for example, things that you have in a data center. You will not have these at the edge. You will have active cooling, but you need to take in account that you have limited space. So you need to dimension your thermal solution or your fan in a decent way that fits the box on the edge. So this is how those are a lot of challenges in thermal solution for the edge. And especially if you look at NVIDIA solution, they are pretty hungry in terms of temperature and power. Dedicated architecture, ASIC accelerator, are much more efficient, result to be much more efficient, 3 to 5 times more efficient with respect to NVIDIA solution. Other challenge that we have at the edge is guarantee security and privacy. So it's true that you don't send data at the edge, but it's also true that your device is subject to physical attacks. So you need to prevent tampering and physical attacks. So feature like root of trust, protection of the model and data are must-have on edge devices. I will talk also about integration, interoperability. So means that typically you deploy neural network on many devices at the edge. And typically imaging, talking about imaging and video, they have different format of exchange of images. You need to be sure that you use standard API. GStreamer is, to mention one, but essentially something that you can exchange format, support different protocol. And I would say the last one, and then I will stop because I've been talking already too much about that, scalability. So as I said, you have many devices at the edge where a neural network needs to be deployed. And you need to manage this complexity. So typically using a software stack that use Docker or they use containers like Docker, Kubernetes is a good option for that. I touch upon a few of the challenges that I see at the edge, but probably there are many more that I forgot.
Yeah.
Thank you, James.
Thank you, Giuseppe. I mean, there are quite a lot of challenges that you've itemized there. But I mean, Faisal, are there any additional challenges that you can think of that you can tell us and warn us about, or maybe any alternative solutions?
Yeah, First of all, I think Giuseppe has sort of more or less covered most of the technical challenges on the hardware side as well as the implementation. He talked about the security because of the large number of devices. You have this end-to-end, you have a need for end-to-end encryption along with the zero trust security frameworks. He also talked about the sheer volume and of the image data, which requires analysis and the filter of the data locally. That means data reduction. He has already touched upon the compute and the latency part as well. I think these, maybe if I could sort of get out of the technical side and then put a bit more broader umbrella challenges. I think one of them is the managing of these multiple devices in the field, then, which kind of poses the operational challenge. Then, unlike a single cloud data center with edge, you might have dozens or thousands of units out in factories, hospitals, or even outdoor locations. So that means maintenance, like updating software, monitoring performance, repairing units, they all become a significant challenge, which requires a high demand for reliability then. Another, I think, the overall broader challenge that I see then is the data governance, which needs to be considered because different regions have laws about very sensitive data, like medical images and personal videos, the way they need to be processed then. So they can pose challenges, especially when you're operating cross-border between different regions. And maybe one other thing which I have sort of experienced, and after talking to several companies as well, but I find a big challenge is a skill gap as well. So edge computing essentially blends expertise in embedded systems. It requires AI, networking, and cybersecurity part. So it's a lot of traditional IT terms, but there's growing demand for engineers who sort of understand the edge AI speciality. But to be honest, they're not quite highly available. So there's a high demand with kind of a shortage around that skill set as well. So there are some technical strategic challenges to allow companies to easily acquire them and build the solutions then.
Thank you, Faisal. I think yeah, it's easy to kind of get downbeat when we're talking about all the challenges that there are, but of course, I mean, every challenge is also an opportunity to innovate. So that's where progress can be made. So it's good times ahead, I think, still. So moving on, I mean that you've given some good advice on how to get around some of the challenges. But maybe first of all we should be considering if they're worth the effort at all. Faisal, how do you differentiate between use cases where edge computing is a necessity and those would just be nice to have in an application?
Yeah, I think this is a really important way to sort of differentiate between the need versus necessity. And we see certain applications where you simply cannot rely on the cloud data due to latency, connectivity, or privacy. And these absolutely kind of require edge processing. And a prime example could be autonomous vehicles. For example, self-driving cars and advanced driving assistance systems like ADS, they are essentially rolling cameras and sensors. They must make split-second decisions, and they can't wait for the data to the round trip to data center. So lives are at stake. If a car doesn't react in milliseconds, this is a kind of a really good example where you have a necessity for an edge computing. You can also think about these augmented and virtual reality systems, say AR glasses. So if you move your hand and the system sort of overlays a graphic, any perceptible lag ruins the experience or causes motion sickness in VR, which is termed as VAC, Virtual Synchronization Conflict Error. A lot of different telecommunication companies, they deploy multi-access edge computing for this particular reason, to enable things like AR gaming or real-time interactive vision apps with latency of just a few milliseconds. I think then you could also think about manufacturing and industrial vision, where you have like on a production line, cameras inspect products for defects. You can think about the healthcare. It considers an AI-powered imaging device in a clinic, for example, portable ultrasounds or an MRI machine. And these devices, they use the AI to analyze the scans in live, and they require sort of an edge processing, therefore, to help the doctors as well. Even something as everyday as smart security cameras, for example, they highly necessitate that. And the modern CCTV cameras often include these onboard vision AI to detect intruders or safety incidences. So these are just a few examples, but essentially any use case where you need real-time reliable vision in spite of the network limits or requiring local control of the data, you can think about as treating as an edge compute essential demand case.
Right, thank you. I mean, yeah, so I mean, as technology advances, I suppose some more kind of true use cases will become more and more apparent as we kind of get what's possible from others. And Giuseppe, how do you deal with the problem deciding this relevance of edge computing as a solution?
So I will add few additional maybe application. Military and defense is becoming quite popular, and drones or tactical decision in remote environment. Agritech is also a good example. Also there, the environment can be remote, and you want to check some of the areas if they can be dedicated to agriculture or not. Sorting of fruits, for example, it's also another typical video analytics kind of application. I will not also underestimate some other application like mission critical application. Well, you can think about satellite. You can think about checking on power grids or pipe inspection in remote places. Those are all applications. They seem very far away, all of these applications among each other. But as a matter of fact, from an AI perspective, they use very similar neural network. And they have the same requirement. So it means probably they don't have a fixed connectivity to the cloud. They need privacy support. They need low latency. And when we talk about low latency, we are talking about milliseconds of answer. Forget to have this kind of application into the cloud and wait for the answer. So there are many applications, but boils down to a similar model to be deployed on the hardware.
And from your point of view specifically, Giuseppe, then, and your experience overseeing the development of integrated circuits for edge computing, what would you say have been the key elements to ensure image processing remains operational and optimal at chip level across the long term?
Okay, now we are entering into a field in which I feel comfortable. I'm an hardware guy. And there are specific hardware features that you need to implement, and they are really intended to specific for AI. So first, you need to work on your architecture of your chip. And the objective are basically two. Flexibility. So you need to support not a single neural network, basically a number of those neural networks, and that's to allow flexibility, and adapt to performance scaling. So have enough compute to satisfy the application that you want, or many applications you want to run upon. Now, few things that we did, at least for my experience and in our architecture and the product that we are putting on the market now as Accelera. We have a multi-core architecture. So what does it mean? That on the same core, so you can map a single neural network on a single core. So you can have multiple neural networks running in parallel, or you can improve performance mapping the same neural network on 2 or 4 different cores. In that case, you privilege performance. So I talk about flexibility. So you need to support multiple, you need to have a relatively rich instruction set to support a large model zoo of your neural networks. You need to have a dynamic load balancing, and this is a feature from the compiler, let's say. And you need to look for how to increase performance and efficiency. We choose for a solution which is based on in-memory computing. In-memory computing is something that has been experimented in the research, and there are different ways of doing memory computing, analog-based or digital-based. Of course, there are pro and contra. I mean, analog can introduce noise, means directly affect accuracy, numerical accuracy of your results. Digital is less efficient, but at least scales with the technology. Okay, so I talk here about architecture choices that we did. Now, I've been already touched about some critical point, thermal design and heat dissipation. All this chip is a must-have. They need a PVT sensors. So means a point into the chip in which you measure power, voltage, and temperature. And based on that, you act. Implement thermal throttling mechanism. So means that if you reach a certain temperature level, the processor automatically reduce the clock speed and the performance. And this to prevent that the chip will be damaged, let's say. Now, there are also a number of things related to process technology and manufacturability and reliability. You need to think that these chips are memory dominated. So more than 60% in our case of memory is SRAM memory. SRAM is high utilized piece of silicon, basically, where the yield is lower than other part of logic of the chip. What does it mean? In order to recover from the yield loss, you implement redundancy. It means that some column the memory are depending on, and is related to which technology node you select, you need to add a number of columns of redundancy such that these can be used in case during the initial testing column are defect and you replace this column with the redundancy one. Very important that, especially for AI chips. Talking about memory, implementing memory beast, so means self-checking mechanism to check the healthiness of the memory. Logic redundancy for the same reason the memory, of course. Power throttling, so means that especially for devices that are, let's say, rely on battery, at a certain moment, if you don't have enough current to run your chip, the chip should go in a sort of battery safe mode. Not necessarily means switching off completely the chip, but going in a so low power mode with lower frequency and probably in a also less capacity to compute, let's say. Okay. And of course, you have some other additional feature related to voltage scaling, dynamic power, and frequency. So you can play on all these topics in order to dynamically decide, depending on the workload, how much power you are consuming. I touch upon a few technical topics, and some of them are specific for AI chips at the edge.
Thanks, Giuseppe. I mean that's great. I think
I may just add one point to what just Yusuf was completing on. I think from our perspective, looking from the consumer side, or actually we're working with a lot of these tech providers, the customers are very, very interested in the longevity support as well. It's one thing to make the chip itself really reliable. That's got to be a very special or an integral part of it. You need specialized accelerator inside as well. You need to make it energy efficient, which is kind of a moving towards this more sustainable AI chips as well. But at the end of the day, it needs to be operatable for a long enough time. So for example, in industries and medical markets, once you install an edge device, you expect to use it for about a decade or more. So the chips that you design then need long-term availability as well as the support. So companies like, for example, NXP, they have product longevity programs which are guaranteeing that certain processes will be manufactured and supported for the next 10 to 50 years time, so the customers can actually have a peace of mind as well.
Thanks for that addition, Faisal. I think that there's a lot of kind of detailed advice there from you both, and so at this point, I think I'll remind anyone watching that you can also view again on demand to kind of recap any information. You can also welcome to send in any follow-up questions live. But if you're watching on demand, you can also send in questions to us at Imaging Machine Vision Europe, and we'll send them on to the speakers. Moving on, from your point of view, Faisal, specifically, working on, well, one of the things you work on is hyperspectral imaging applications. What would you say are the main benefits of edge computing there that they've delivered to hyperspectral use cases?
Yeah, so some of the benefits, actually, in a way, Giuseppe earlier on mentioned them too, but hyperspectral imaging is a perfect example, in my opinion, especially where the edge computing makes a dramatic difference. Just to set the stage for everybody who's not familiar, so hyperspectral cameras capture hundreds of wavelengths per pixel. So they're creating extremely rich images, and the data volumes are huge, often on the order of, let's say, 1 gigabit per second for a single camera. So historically, dealing with that meant storing piles of data or trying to stream it to a powerful remote server, which isn't practical in many scenarios. And so edge computing there allows you to process and compress that data on the fly, right where it's collected. So one major benefit, for example, for the real-time analysis is in the field. For example, you can put an edge computing module on a drone or a tractor that's carrying a hyperspectral imaging camera over farm fields. And instead of just recording the data to analyze later, the edge processors can then run machine learning models in real time to identify the crop stresses. They can identify different disease indicators in the spectral data. And they're detecting issues like fungal infections on plants very early on site, even before human eye would notice anything unusual. And the farmers get an immediate alert like this section of the crop shows the spectral signature of disease, and they need, or this requires more watering, and they can act quickly. And without the edge processing, you would have to send all that raw spectral data to a lab or a cloud and maybe wait for hours or even days for results, and by which time the issue might have spread. So essentially, edge computing turns hyperspectral imaging into an actionable real-time tool then, rather than just a data collection exercise. Another benefit that you can think about there is a drastically reduced data transmission. So the example was given by Giuseppe earlier as well, but think about the satellites, right? Or a high altitude drone which are going around the Earth observation. And it's either impossible or sometimes extremely expensive to send the raw hyperspectral imaging data over the air. With edge computing, then you can progress and distill that data before you send it over down to the base stations. And these, what you then deploy is this AI-based compressions, and they can achieve now very effectively up to 60, 70, 80, 90% data dissection for these hyperspectral streams as well. This is what Canadian Space Agency is doing in their hyperspectral imaging in the real time in the orbit too. So we are also seeing several tons of different use cases when it comes to industrial application. Take recycling, for example. You can think about the benefit it provides in terms of autonomy and the resilience. These imaging often is done in a pretty remote or mobile scenarios like wildfire monitoring in forests or geological surveys in the deserts, even in the military surveillances with aircrafts. And their edge computing allows the analysis to happen locally in the system without ever having to rely on the networking with the cloud services. Then, so there are tons of advantages in all of these applications where you practically actually can see them. And in summary, you can say that what it provides is that real-time insights, it significantly cuts down on all the data transmission requirements, and more importantly, it enables the deployment in bandwidth or connectivity constrained environments. And so you're no longer relying on external factors in order to run your process system.
Yes, yeah, agree. There's a lot of cross-applicable cases there, kind of with hyperspectral and edge. They go hand in hand all the time. So I'm going to ask you to look into your crystal balls for a moment and tell me how you think image processing applications that leverage edge computing will evolve over the next few years. Maybe Giuseppe, you could take that one on for me first.
Yes. Let me start before looking into crystal balls into what is the prediction of the market. So how big is the market for edge computing? In 2024, more than 6 billion was invested in edge computing. Now, if you look in 2025, edge computing market is estimated in 14.5 billions. And we expect a growing year to year of this market of around 20% until 2032. So, and in terms of usage and adoption of edge devices, think about that in 2026, edge computing is expected to be 75% of the enterprise data processing with latency that is under 5 milliseconds. There is a problem here. With 75 billion connected devices expected globally, we need to handle more efficiently the devices and the processing. Okay? So those are a few numbers that I want to give. Now, where are we today? Today we are in data analytics, visual understanding, predictive AI. We are starting in generative contents. Generative AI is moving to the edge more and more. This is valid for video, is valid for LLMs, but it's another topic. Tomorrow we see that from creation of contents, system will be able to do independently intelligent decision with minimum latency and power consumption. Okay, so think about autonomous vehicles. What will happen? Think about industrial system, and real-time quality control that we were mentioning before. Think about diagnosis on healthcare devices. Those are things that will become the normality. Okay. Now, what we have on the table in terms of technology, we are moving in more efficient ASIC accelerator for AI. So there are few players on the market. We are moving into vision transformers that are becoming quite popular respect to traditional CNN. Those are things that are popping up in the now, let's say. Now, emerging areas, I would say it's very promising, especially if you talk about efficiency, what will happen with neuromorphic computing. So the brain-inspired kind of architecture. Actually, few examples are today present. Intel Loy, which has 10 million of neurons. IBM and North which has 256 million synapses. Of course, nothing compare what the real brain has today, but they are showing impressive results in terms of video analysis and performance. The other topic is related to integrate AI devices together with photonics for chip integrated sensing. I think this is also a big topic. This is showing already that you can potentially compute 100 billion of pixels with a response of nanoseconds. We have been talking now in milliseconds. We are going to nanosecond space. And it opened another completely field of application, real-time application. I stop here, but I just gave, a view of what is today, what is the next future, and what is a little bit farther away from us, but very exciting. Thanks.
Thanks, Giuseppe. And Faisal, what have you got fixed in your sites? What's waiting for you on the horizon of edge computing based image processing, do you think?
Right. In the trends that we see, the market analysis has already been provided. So without going into it, and even the technical side, which we discussed about the better hardware, more power efficiency, efficient AI, more sustainable. What I think I anticipate is in terms of the applications that I see around and the pop of the AI utility in various different use cases, I foresee that at least the real-time video analytics would be almost everywhere. Its trend is moving beyond just analyzing still images to analyze live video streams at the edge. So whether it's analyzing customer behavior in the retail stores or traffic monitoring in smart cities, real-time vision on the edge devices will be kind of proliferating the market. And this becomes even more deployable because of the 5G and 6G, eventually 6G networks. We are already seeing these cloud providers like AWS, which are offering these local zones with single-digit millisecond latencies, essentially sort of bringing the cloud closer to you rather than you having to run towards cloud for the processing. Then, so it's going to be very much application specific, but you can actually see these markets shifting between one much closer towards the edge, purely edge, or actually bringing the cloud towards the edge wherever it's needed. When I think one of another key challenge, not a challenge, but key trend that I'm seeing in the market itself and the way we sort of see towards future development as well is the integration and the standardization. So today, you see these deploying an edge solution can be a bit custom. So you need to find a really good use case, fit the hardware around it, and then tweak it for the application. So it's a lot of tweaking and of hardware in the software side. And I think what we'll see is more integrated solutions, for instance, smart camera products that come with built-in edge AI capabilities that you can just configure for your needs. So you have the entire capabilities already deployed in the device, and then you can just tweak it to cater for your application needs. And so this way you can see quite a large number of trends, but whether it's ubiquitous edge AI, hyper-efficient edge hardware, edge cloud kind of a convergence in terms of markets, new application domains with AR navigation and ADS assistance for vehicles, or improve management and reliability as well. So how do you sort of cater with that? All of these sort of point towards much more, you can say, consumer oriented, but more standardized versions of the deployment of the edge AI across markets.
Right, and moving back slightly to the discussion about spectral imaging and the possibility of fast scanning and processing, we've got an audience question that's come in now, which asks, is there any vision system capable of detecting small car damages efficiently, like a 4mm dent, for example, or would this require a longer processing time? That's not directed to anyone specifically, but maybe Faisal, you might be best placed for that one.
So sorry, just if you could repeat that for my understanding. The question is if there's a vision system capable of detecting a 4mm dent in a car.
Yes, yeah. Or require a longer processing time, that system.
Well, absolutely there is. It's just that has it been used as an application? I don't know about that. So the limitation of detection is very much sensor dependent and how the optics is deployed. Then the processing of that is sort of comes afterwards. So the first thing is the collection of the data. How what's your spatial and the spectral resolution. That determines the amount of differentiation that you can create, or a resolution that you can create between an object, in this case a dent, for example, from a normal surface. But you can think about surgical applications where hyperspectral imaging is used to distinguish between seemingly perfect tissue, whereas one is cancerous and another is not. So yes, capability wise, absolutely, there's nothing stopping you from doing it. I just don't know whether there's an application or somebody's specifically looking at this as a use case. It might, or you might just have to produce one.
I can add something. We have been proven, I'm talking about the platform that we are using and I'm using every day. We have produced a demo with 8K camera, pretty expensive one, I must say. And talking about, you can find a small part, it depends on the resolution of your video. 8 camera, real-time processing, distributed all the data images on 2 of our boards, on 2 of our chip. We were able to do detection of, yeah, probably a single things that was 100 meters away.
Yeah,
which is even more challenging of what the
dent is considered.
Yeah, so
yeah,
that's
yeah, 4 millimeters is quite a big area. It's
yes.
It's
and actually the detection, if we are talking here about detection, can be very smart. Think about combining different neural networks. I mean, I saw some application, and maybe can be also an inspiration for the audience. There was a combination in a complex imaging pipeline with two neural network. One was pose estimation, so how your body is represented, and a zooming into object detection of what you have in your hand. Think about you are eating at the table, you have a knife on your table. It's not a dangerous situation. Think about I take my knife and I point against another person. That's a different story. I mean, you have several levels in the video, several levels of smartness where you can detect what is happening in a situation. I gave just few examples that for me are representative for how AI can be smart nowadays. There are many more and more ethical, compliant, like we were mentioning about the images. The images in health and in surgery and medicine are pretty high resolution, let's say.
Right, right. I wanted to ask, if we've got time, just squeeze a question in the middle here about hybrid cases, and if there's any advantage in terms of efficiency of balancing what stays on the edge and what's pushed out elsewhere. Where does that balance point tend to be, and has it shifted over the last few years, maybe? Anyone can take that on, yeah.
Okay. Yes, you always actually have to balance that. No matter what application you are trying to develop, as long as you have a really good, clear, valuable use case and you define your problem well, I think that's where then you can define type of technology that might be sufficient to produce that. Now you can always overkill a product. You can kill a bird with a bazooka as well, but do you actually need to? So it boils down to what your specific needs of a particular application or a product are. As long as you can very clearly define, then you can break it down further into the needs, whether you actually need a hyperspectral camera, RGB would be enough or not. Do you need edge computing? If you even need edge computing, do you need to deploy it all? With how many accelerators would you need? Would you need to use GPUs or not? I think these are the questions then you distill down based on the application requirement. And always my recommendation would be to start with a really good problem statement. As long as you have a really good problem statement, you can sort of deduce the answers from there backwards then, and then you can come to the specification of a technology that might be sufficient to produce that. Often people, what they do is they start with amazing technology, and then they try to distill down into where we're going to apply it. And that's a really backward way of solving a problem. And it actually costs you a lot as well. At the end of the day, everything has to be to make budgeted sense. Then if you're going to make $1 million product, but nobody is willing to buy it because it's just too expensive, it's a waste of resources. You want to do you just introduce sufficient technology to solve perfectly the use case that you have in mind. You don't need to spend more than that. And all the compute power, all the spectral resolution, all the computational power comes at the cost. You want to mitigate or reduce it as much as you possibly can.
And the edge market is very fragmented. Are you going to implement something very close to your sensor, to your camera? Are you going to use a gateway that collects a number of streams of camera? So those are completely different compute requirements. Nowadays, you have choices, but I agree you should not overdo in terms of technology, because then you end up in a way too expensive solution.
So I'll summarize in maybe one sentence then. I would say start with a focused use case. Use your available tech. Don't overcomplicate it. Keep your security and resilience in the mind when you're producing the product. List down the hardware which is sufficient to just deliver that. And learn by doing small pilots. Don't just overdo it or jump into the big projects then.
And maybe something on the top, build incrementally. So if you have a project that you find, start small, build incrementally. Use the right software stack, something that is stable. Engage with community. It's also very important. I mean, think about community today, about Arduino, Raspberry Pi. Those are environment that allows you to deploy, to use together AI edge solution with this kind of platform will help a lot. You will find a lot of examples to build upon.
Great. Well, thank you both for your time there. I think we've almost run out of time on that one, but there's just time to say that we ventured quite close to the edge, both in the discussion points, and we've almost run out of time. But before that happens, there's still time to mention that the panel discussion will be available on demand in the website section. So go along and check those out. And to get your nominations in for the Photonics 100 before the deadline closes at the end of the month. The next discussion we've got lined up in the Visionary series will be streaming live on Wednesday, the 16th of July at 3 p.m. We'll hear from experts including Tom Pickering from ANSYS CMAX, Chris Maloney from VPI Photonics, and Dave Jacobson at Lambda Research on using optical software to enhance both accuracy and efficiency. So sign up for that and look out for that one now. But for now, there's just time for me to thank our guests again, Giuseppe and Faisal, for joining, taking the time to discuss the topic. Thank you both. Thanks.
Thank you.
Thank you, James. Thank you.
Take care.
Bye. Take care.
Bye.
Bye-bye.